Hi everyone, my name is Chuck and I'll be going over section handout number 11 on perceptrons and logistic regression. The way that this discussion section review video will work is I'm going to go over the basics of the perceptron algorithm, then we'll dive into the first problem on perceptron and then the second problem on logistic regression. With that, let's get started. So the general setup of the machine learning problem on perceptron works is you have a set of data points x and you want to find the label y and you want to be able to predict it correctly. And so this problem is known as classification in machine learning, where we're trying to separate our data into separate classes. And the way we do that is we use a model called Perceptron. And an example of a problem in classification is like hot dog versus not hot dog. And one of the main caveats about Perceptron is that to even consider this algorithm and whether or not we want to use it, the data must be linearly separable. And what I mean by that is, let's just say here's your data. All the positive examples and the negative examples, you must be able to draw a line that separates the positive and negative examples. And in higher dimensions, you must be able to draw a hyperplane to separate the positive examples and the negative examples. Now, the way that the pipeline generally works in machine learning for classification is you're given an input data x, so this is called your data, and you want to featureize your data so that it has real, discrete, or continuous values. And you want to apply these numbers through a model, S of f of x, in which case for perceptron is just a dot product between your weights and your features. And then you want to calculate a prediction y hat, which is just the sign of w transpose f of x in the perceptron case. And then finally, you want to measure how close or accurate you are between your true label y and your real output or your prediction y hat. And this is called the loss function. And so in reality, you know your data x, you know your features, you know the correct label y, and you typically design the model S and your loss function L, and you want to minimize L. And so the only hard part is how do we find W? So the way to find W is with this algorithm described over here. So we would initially set our weights to be 0, and then for all of the data points and with all of these features, we're going to first take the dot product as we see over here. Then if our predicted sign of the dot product is +1 and the value actually is +1, then that means that we've classified the point correctly, and the same for -1 and -1, then we don't do anything because we don't fix what's broken. And however, if our predicted label y hat is wrong, then we're going to have to update our weights with this update formula, which is our new weight w is equal to w plus the correct label y prime multiplied by the features. And until we get all the data points correctly, we have to rerun this step number 2 of the algorithm multiple times until all of our points are able to be separated by a line. And with that, let's cover a couple of intuitions of what the dot product means and what the update rule means, and finally the bias feature. So first, what does the dot product mean? Like, why do we even use the dot product? Well, if we look at this example here, right, a correct W would be like this W. And the reason why is because W transpose f of x is really equal to the Euclidean norm of W f of x times it by the cosine between W and f of x. And we can see that the Euclidean norms are always positive, which means the only value that determines the sign of this equation, which is really the y hat. And so the only value that determines the y hat is the cosine of w and f of x. And so if we look at the graph of cosine, we can see that cosine is positive between values of 90 and -90, which means that if our angle between the w vector and the f of x, so here's x1 and x2, so is positive, then we label it as positive. While if the angle is greater than 90 degrees away from the w vector, then we're going to be labeling it as negative. And so all the points over here are labeled as positive because the dot product between w and any point here is positive because the angle between any two vectors on this side of the hyperplane is going to be labeled as positive. And the last definition that I want to clarify is that this line is called the decision boundary. And the reason why it's called a decision boundary is because you're making a decision of whether or not your label is positive or negative. If you're on the right side, it's positive. If you're on the left side, it's negative. And in higher dimensions, it's also called the hyperplane. And it's the value where the cosine of the angle is 0, or where W transpose f of x is equal to 0. And so that is the geometric and mathematical intuition behind why we're using the dot product. And now let's talk about why our update rule even works. So our update rule is guaranteed such that if we run it enough times through all of our data points, it will converge to the optimal value W if and only if our data is linearly separable. However, the main thing that we have to note is, and try to understand, is why intuitively this algorithm works. So we don't have to prove that it actually converges. I believe it's outside of the scope of this course, but let's just try to understand intuitively why this algorithm works. So the reason why this algorithm works is because, let's just say our predicted value y is -1, or sorry, it's 1, and the real value y is actually -1. And so what this means is that the sign of W transpose x is positive when it should have been negative, which means that we need the value of W transpose x to go down. And so in order for the value of W transpose x to go down, what we do is we update x with this rule. W minus 1, because the true value of y is -1, times it by f of x is equal to the new value. And if we multiply it and evaluate out the new W prime x, we're going to get W minus f of x transpose times f of x. And we see that this value is really W transpose f of x minus f of x transpose f of x. And this is actually equal to minus the Euclidean norm squared of f of x, which this value is always positive, which means the negative of its value is always negative, which means that we're actually decreasing the value of W transpose f of x by subtracting it from a value that is always positive. And so, even though this value may be positive and incorrectly lead to the incorrect prediction of y hat being positive, our new updated value will be lower, and hopefully it will be less than 0, so that our prediction can actually be -1 as opposed to +1. So that's why the weight updates equation works intuitively. Finally, let's talk about the bias term. The bias term essentially makes it so that our decision boundary and our hyperplane and our weight vector no longer have to go through the origin. And what I mean by that is, if we take a look at the equation W transpose f of x, we see that no matter what, if we set this equation equal to 0, which is the equation for our decision boundary, we can see that the weights 0, 0, 0, 0, or essentially the 0 vector, will always be a valid solution, which means that our weights always have to be passing through the point 0, 0, 0. However, if, let's say, a negative value was at this point, right? Or a negative value was at this point and a negative value was at this point, right? We would need our weights to not pass through the point 0, 0, 0, 0. And so we're going to be adding a bias feature so that our weights can start somewhere else along the y-axis, so that you can find a decision boundary that looks something like this, that is orthogonal to your weight vector that now starts at a new bias feature. And so we're going to be changing our W to be equal to something like this. And f of x is really equal to, this should be b, or W0, and f of x is really just 1, x1, x2, xn. And so that's what the bias feature really does. It makes it so that your weight feature and your hyperplane no longer have to go through the origin. With that said, let's start into the problems now. All right, let's get started with question 2, Perceptron. So if you haven't had a chance to read the question yet or attempt to solve it, please pause this video and read the questions and try to get the main idea of this problem. So hopefully by now you've gotten the gist of this problem. What this problem is asking is that you have these set of movies and you want to predict if these movies will be profitable or not. And in terms of the data pipeline that we described above, the algorithm is technically that you're given an X, which is just a movie, and you're going to featurize X by generating two separate critic scores, A and B, which take on values between 1 and 4. And you're going to be applying it through a function S of f of x, which computes the dot product between W and f of x. And this is the Perceptron algorithm. And to get your predicted value, y hat, we're going to be taking the sine of S of f of x to get our prediction. And finally, we're going to be comparing it against the true y value, which is your label. And what we can see is that our f of x's and our y's are always given to us in the training data. And so what we are trying to determine is how to find this W. Now, before we even attempt to find this W in the Perceptron algorithm, question 2a is asking you if we should even use the Perceptron algorithm at all. And we should only use the Perceptron algorithm if our data is linearly separable. So, to determine if our data is linearly separable, an easy way to do so for 2D problems is that we can just plot our data and see if we can draw a line that separates the positive and the negative examples. So let's do that. We have our point at 1, 1, our point at 3, 2, which is positive, our point at 2, 4, which is positive, our point at 3, 4, which is positive, and our point at 2, 3, which is negative. And if we look closely, we can actually draw a line here. And this line is called a decision boundary that separates the positives and the negatives. And the reason why it's called a decision boundary is because you're making a decision at this line. Anytime you're on the left of this line, your points are classified as negative. Anytime you're on the right side of this line, your points are classified as positive. Now, where the weight feature lies is the weight feature always is orthogonal to the decision boundary. Now, this is just one place that the weight feature can be because the bias term can change the places where the weight feature lies along the decision boundaries. For example, another valid weight feature may lie here. Now, given that we know that our data is linearly separable, we can now use the Perceptron algorithm to find this W. Sure, we were able to find it graphically, but we want to find it numerically. So that is what question 2b is asking. So question 2b is asking you to use the algorithm described above here in Perceptron. And we're going to run through this algorithm in order to find the correct W that classifies your data points correctly for all your training data. So let's do one pass through the entire data with the Perceptron algorithm above. And just a review of how the Perceptron algorithm works. The two main parts is that first we have to compute the dot product, S equals W transpose f of x. And we have to get our prediction, y hat equals sine of S. And if our prediction is correct, then continue. We don't have to do anything because we don't fix what's broken. And if it's not correct, then we have to change the value of our W transpose f of x to make it go up or down, depending on the true label y. And so we use our update rule, W plus y f of x. With that, let's jump right into this algorithm. So our initial weights are going to be -1, 0, and 0. And what these weights corresponding to is these two weights corresponds to your feature A and feature B, and this weight is actually corresponding to your bias feature, which is always going to be 1. Now, with that said, if we compute the dot product, we're going to get a value of -1, which means that we're going to be predicting the first data point for first movie pellet power as not profitable, which is correct. And because it's correct, we're going to not do anything and keep the weights the same. Now, a key note about the initial weights is that these set of initial weights are always going to label everything as negative or not profitable because the bias feature is negative and because the weights are all 0. And so it's always going to produce a not profitable, which is good for our first example, but for our second example, we can see that if we compute the dot product, we're going to get -1 times 3 plus 0 times, or sorry, -1 times 1 plus 0 times 3 plus 0 times 2, which is going to be -1, which is actually not correct because we predicted it to have a negative sign, which means we predicted it to be not profitable, but it actually is profitable. And so because of that, we have to update our weights with the update rule, in which case our new weight is going to be equal to -1, 0, 0, plus the correct y value, which is 1, multiplied by the features, which is going to be 1, 3, and 2. And so if we add these two vectors together, we're going to get a weight of 0, 3, and 2. Now, so our new weights are 0, 3, and 2. And if we compute the dot product between these new weights and our third movie's features, we're going to get 0 times 1 plus it by 3 times 2 plus it by 2 times 4, which is going to be 14. And we're going to see that this is correct because this value has a positive sign, which means we predicted as profitable, and it is profitable. And so because of that, nothing is broken, and so we do not change the weights. Likewise, for example 4, we have the same weights, 0, 3, 2. We compute the dot product, 0 times 1 plus 3 times 3 plus 2 times 4, which is 17. And again, we see that this is correct because the value is positive and we predicted it to be profitable or positive. Now, finally, we have our last example or last training point where our weights are 0, 3, 2. And we compute the dot product, 0 times 1 plus 3 times 2 plus 2 times 3, which is 12. And we see that this value is positive, so we predicted it as profitable, but it's actually not profitable. So it's not correct. And because of that, we have to update our weights with the update rule. So we get 0, 3, 2, which is our old weights, and we add it to the real value of y, which is -1, multiplied by the features, which is 1, 2, and 3. And because of that, our new weights are going to be -1, 1, and -1. And so our final weights are -1, 1, and -1. And if we plot these weights over here, we can see that the vector -1, 1, -1 is actually this vector, where -1, the first -1 is really just the bias along the y-axis or b-score, and we want to go 1 up or 1 to the right and -1 down. So our true vector, if we graphed it, our weight vector is this vector here. And we see that its decision boundary and its separator is this decision boundary. This decision boundary is our decision boundary created by our new weights. And sorry, the line here is not too straight because graphically this graph is a little oddly shaped, but this in reality is a straight line. And so all points on this side of the graph will be labeled as positive, including the point on the line, because the sign is labeled as greater than or equal to 0, and all the points on this side of the data will be labeled as negative or not profitable. And so if we look at question 2C, question 2C is asking, after one iteration of the algorithm, have the weights been learned to separate the data? And we can see that the answer is no, because even though this point is classified correctly because it's on the line, and these 2 points are classified correctly because it's on the opposite side of the weight, we can see that these 2 points are actually incorrectly classified and will be labeled as negative. And we can actually see that result numerically by plugging in the weights -1, 1, and -1, and multiplying it or dot producting it by the data of data point 3 or data point 4. We'll just be doing data point 3, where we'll be getting 1, 2, and 4. And we can see that this value is going to be -1 plus 2 minus 4, which is going to be -3. And -3 has a negative sign, which means that we are predicting that this movie 3 is going to be not profitable when it actually is profitable. And so our weights have not been learned to separate the data because it misclassified movie number 3. And so, no, we have not been able to find the W that separates the data. Yet. So if we keep on running this algorithm through the data points, after many iterations, it will find the correct W. Now, with that, let's go into question 2D. So question 2D is asking you, given some specific rules about the feature, irregardless of what training data is given to you, as long as the training data follows the rules of the feature, is the training data going to be linearly separable? So there are 3 separate scenarios, and this is actually a crux of determining if or if not we want to use the Perceptron algorithm or not. And so we want to determine if the data is going to be linearly separable. With that, let's look at question, the first question, or A. It asks that, and it says that your reviewers, if their total of their scores is more than 8, then the movie will definitely be profitable. And if we just do it graphically for 2D, we can see that for all these examples, it generalizes into higher dimensions as well. If we graph our x1 score and x2 score, we can index it by 2. If any of our data points fall on this side of the graph, meaning that the total of their scores is more than 8, then we will label it as profitable. And if the sum of the scores of the reviewer is on this side of the decision boundary, which means that the sum of their scores is less than 8, then the movie will be labeled as not profitable. So we can see that we can clearly draw a line through the graph such that the positives and the negatives are separated. And so the training data, no matter what data you pick, as long as it follows the rule that the sum and total of their scores is more than 8, then the movie will be profitable. Then this set of rules is always going to be linearly separable. Now, let's go into question B. So your reviewers are art critics, and your movie will be profitable if and only if each reviewer gives a score of 2 or a score of 3. What this rule looks like in the 2D feature case is if your score is a 2 or a 3 for all your critics, then it will be positive labeled or profitable. Everything else is going to be negatively labeled. And as we can see from this graph, the correct classifier needs to look something like this, and that is clearly not a line. And because it's not a line, we can see that we can pick a certain set of training data points, such as this example that we've seen here, so that these feature rules are not linearly separable, and so this data set cannot be used on the Perceptron algorithm to find the correct W. So this is no, and this is yes. And for question C, your reviewers have weird but different tastes. Your movie will be profitable if and only if both reviewers agree. And so we can see that these rules confine the positive examples to lie alongside this line, where the x1 and x2 values all agree. And we see that everything else will be labeled as negative. And even though this is a line, you actually need 2 decision boundaries to separate the negatives from the positives. And because we need 2 and not 1 line to separate the negatives from the positives, we can see that this is also not linearly separable, and so the answer is no. Started on question 3, optimization. This question is a question about logistic regression, which applies the perceptron combined with an activation function known as sigmoid. And if you haven't been able to read or try this question yet, please pause this video right now and have a look at this question. Alright, hopefully by now you had a chance to at least look at the question. So with that, let's dive into the problem and what it's asking. So you're given some data set and you have n samples or n training data points, and each data point is a k-dimensional feature vector composed of k individual features. Now you want to find a function h of x such that you are mapping your original input data x into a probability space which outputs the probability that the output label y is 1 given your input data x. So the real output label is always going to be a discrete value that is either 0 or 1, and that's your y. Now, however, your prediction y hat is going to be a continuous value between the range of 0 to 1, which simulates the probability that we think our label is 1 given our input data x. Now, in order to model this probability, we have to apply a function s of gamma equals 1 over 1 plus e to the negative gamma, also known as the sigmoid function, in order to squash our outputs w transpose x into the continuous range of 0 to 1. And let me just talk a little bit more on what the sigmoid function does. So originally over here, we have our W transpose X, or our original perceptron algorithm. The sigmoid algorithm, or the sigmoid activation layer, does two things. The first thing that it does is it squashes W transpose X, which previously could have taken any value between negative infinity and infinity, to a probability that lies between the continuous space of 0 and 1. In fact, we can take a look at this graphically. If we see, here are the values of W transpose X, and here's the value of S of W transpose X, which is really our y hat prediction. And we can see that if W transpose X is 0, then our sigmoid function is going to output a half. And if our W transpose X goes all the way to infinity, then we can see that our y hat and prediction will be 1, or 100% probability. And if our W transpose X goes all the way out here to negative infinity, we can see that our y hat, or prediction probability, will become 0. So this is what the sigmoid activation function looks like. There are many more activation functions like softmax and ReLU, which you will see in future projects and future worksheets. And so the second aspect of these activation functions is the also introduced nonlinearity to the original perceptron algorithm. And nonlinearity is important because originally the perceptron algorithm only worked if the data was linearly separable. But now the data no longer has to be linearly separable. With that, let's go into how do we measure the closeness of our prediction y hat with the value y. So after we apply our logistic regression model, we feed it in an input x, which we know, and we get a prediction y hat. We want to know how close our value y hat is with the original value y. And we want to penalize our model if the difference between y hat and y is large, and we want to essentially keep our model the same if the difference between y hat and y is little. And so the way we do that is we assign a score, or a loss, to our prediction y hat. And so the loss function is shown here in this equation, and this function is known as the log loss function, or binary cross entropy. And if you're interested in how this function works and all its intricacies and what it really means, there will be a link below in the discussion videos, which talks a little bit more on how this function came to be and its roots in information theory and so on and so forth. But obviously this is all additional information and you don't need to know it for this course. It's just nice to know as additional information if you want to understand the true meaning of how this function came to be. Examples on the log loss function to gain some more intuition of how the log loss function really works. So we can try different values for y and y hat and their losses. So if our true label y is 1 and our y hat is 0, meaning that we predict that there's a 0% chance that y is actually 1, yet it turns out to actually be 1. If we work out the math and plug y and y hat into this equation, where y hat is equal to h of x, we're going to get our loss to be infinity, which is a extremely high and big number for the loss, and that's really bad because we want loss to be as low as possible, because the loss measures how close we are in theory to between our y hat prediction and the true label y. Now if we try a value like 0.1, where we're saying there's a 10% chance that y is 1 given our data x, then we can see that our loss is about 2.3, which is still pretty high, but it's getting better. Now, if we get our value y hat to be prediction value 0.9, then we can see that our loss will be around 0.1, which is really good. Finally, if we have our y hat become exactly equal to 1, meaning there's a 100% chance that y is 1, and the label y actually is 1, then our label and our loss will be 0. Now, we can try it for the opposite value of y as well, where y is false. And we can see that the loss here is 0. The loss here is 0.1. The loss here is 2.3. And the loss here is infinity. So it's almost like the reverse case when y is 1. And a key thing about the log loss is it penalizes overconfident estimations. So if you're overly confident, right, and you say that there's a 0% chance that y is 1, and y ends up being 1, then your loss will balloon up to infinity. And so you don't want that ever to happen. And so you oftentimes always assign probabilities that are closer to the range of 0.5 than 0, or than you would typically do. So with this intuition about the log loss function and the logistic regression model, we can see that given any data point x, we can generate a prediction y hat, which tells us the probability that we think our true label is 1 given our input data x. And we can test how close this true probability is, y hat is, against our true label y by applying it through our loss function L. Now, the only thing that we still have left uncovered is how to find the correct w, such that the y hat is closer towards the correct label y. So the way to find the correct value w is we're going to use an algorithm called stochastic gradient descent. And the intuition behind stochastic gradient descent and the formula for it is w equals w minus eta, which is the step size, multiplied by the gradient of the loss function with respect to the vector w. And all of these are done in higher dimensions, like where the dimension is k or where the dimension is d, for example. And for the one-dimensional interpretation of gradient descent, it's really equal to wi equals wi minus the step size times it by the derivative of the loss with respect to wi. And now the intuition behind stochastic gradient descent is, let's just say you're trying to minimize the function L equals w squared. And so you have this function here, w squared, where this value is around 0.5, and here is, let's just say 0.4. And we choose our step size to be, let's just say 0.1. So the way this algorithm works is we start at initial point w equals 0.5, and we want to go all the way to the bottom here. And we want to get our w to eventually be equal to 0, where the loss function is minimized. And so the way that we can do this iteratively is we apply this formula multiple times. And so here, the derivative of L with respect to w is 2w. And so we set our new w prime equal to the old w, 0.5, minus the step size multiplied by 2 times the old value of w, which is going to be 2 times 0.5. And we can see that this value, if we evaluate it out, is going to be 0.4. And so we're going to be moving our value w 0.1 directions this way. And so our new w will be here, and our loss will be around here. And so this is the way that our loss function has decreased, and our W has shifted. And we want to slowly move until we arrive at the optimal W and the lowest L. Now, a caveat here is that the step size that you choose is very important. For example, if eta, your step size, was set to 1, then we would have jumped all the way over here, and we would have skipped actually the correct value for W. So we don't want eta to be too large, and we don't want eta to be too small, because it would take too many steps to converge to the correct point. So this is the heart behind the stochastic gradient descent algorithm, and it's going to be what we're going to be using to find the correct value of W. Now, given that as a background, we need to be able to find the derivative of the loss with respect to the Wi, which is why in part 3a, we're finding dl dw of I. So, how do we find dl dw of I? Well, we're going to be using something called the chain rule, which lies behind the heart of backpropagation or auto-differentiation. And the heart behind how chain rule works is we don't want to evaluate complex derivatives, and so we're going to substitute and break down our equation of a complex derivative into smaller and simpler derivatives that we know we can calculate easily. And just a simple example to warm us up is, let's just say z equals 5x minus 3 and square root of this. How do we calculate dz dx? Well, what we can do is we can transform this equation into two simpler equations, such that we let u equals to 5x minus 3. So we have z equals u to the 1/2 and u is equal to 5x minus 3. Now all we have to do is find dz du and multiply that with du dx. So here, dz du equals 1/2 u to the negative 1/2, and du dx equals 5. And so if we plug it into this equation over here, we have 1/2 times 5x minus 3 to the negative 1/2 times by 5, and that is equal to dz dx. So essentially, we're going to be doing the same thing for a little bit more complicated equation, and all we're doing is substituting our complex equation with smaller and simpler equations that we can easily calculate the derivative with. That's all the chain rule does and all the backpropagation / autodiff algorithm does for logistic regression and for neural networks and so on and so forth. So let's begin. We have here that our loss is equal to negative y ln h of x plus 1 minus y by ln of 1 minus h of x. And we want to find dl dw of I. Now, we're going to define some auxiliary variables and simpler equations that we can actually calculate and evaluate. So first, we're going to note that y hat is equal to h of x, which is equal to s of w transpose x, which is equal to s of gamma, which is equal to 1 over 1 plus e to the negative gamma, which is really equal to 1 over 1 plus e to the negative w transpose x. We're just writing out our prediction y hat in as many ways as possible so that it's easy to substitute it in later on. Now, we're going to write our value L is equal to negative y ln of y hat plus 1 minus y times it by ln of 1 minus y hat. We're going to set y hat equal to s of gamma, which is going to be equal to 1 over 1 plus e to the negative gamma. And we're going to set gamma equal to W transpose X. Now, with this, with these set of equations, we can calculate the derivative of all of these equations with respect to the only other variable in these equations. And so we're going to get dl dy hat. Keep in mind here that your y label is a constant because that's given to you in the training data. And so we're going to get this is equal to negative y over y hat plus it by 1 minus y over 1 minus y hat. And we're going to get dy hat d gamma is equal to ds of gamma dy hat, which is really equal to 1 over 1 plus e to the negative gamma times it by e to the negative gamma over 1 plus e to the negative gamma, which is really just s of gamma times 1 minus s of gamma. Over here we use the hint described above, which is really just y hat times 1 minus y hat. And finally, d gamma over d of wi is really d of summation I equals 1 k of wi xi over dwi. We should use j just to not confuse the variables, and because there's only one x of I that is multiplied by wi, the derivative just becomes x of I. And so if we plug these three equations using the chain rule into the dl dwi, we're going to get dl dwi is equal to dl dy hat times it by dy hat dy times it by, or d gamma, which times it by d gamma dwi, which is really equal to negative y over y hat plus 1 minus y over 1 minus y hat. Oh, sorry about that. I actually made a mistake in calculating the derivative over here. This should be a minus because we're taking the derivative of ln of 1 minus y hat, and so it's minus 1 minus y over 1 minus y hat. And so the value here should be negative, and we're multiplying that by dy hat over dy, which is y hat times by 1 minus y hat. And we multiply this value by x of I. And if we simplify this out, this value is going to become negative y by 1 minus y hat minus 1 minus y multiplied by y hat times it by x of I. And if we simplify this out even further, we're going to get the value negative y minus y hat minus y hat plus y hat x of I, which is just going to be, since these two values cancel out, negative y plus y hat times it by x of I. So that's our derivative of L with respect to W of I. And now, if we just plug this value into the equation W of I, we're going to get our stochastic gradient descent update rule using this formula over here. So that W of I is equal to W of I minus eta times it by dl dw of I, which is really W of I minus eta times it by negative y plus y hat times by x of I. And if we substitute it in the h of x, just to make it more similar to what you'll see in the solutions, this is really just h of x minus y times by x of I. So that's how you would generally solve these questions on logistic regression and stochastic gradient descent. The main takeaways is that if you apply your perceptron algorithm coupled alongside a nonlinearity function, such as the sigmoid on the outside, you'll get a logistic regression model, which outputs the probability that you get y to be 1. And in order to determine the closeness of your prediction with the real value y, you would apply it through a log loss function. And to find the correct weights and parameters for your model w, you would need to apply the stochastic gradient descent update rule and calculate the derivatives. And again, to calculate the derivatives, all we use is the chain rule, which is the backpropagation algorithm, and we apply the chain rule multiple times in order to get this nice update rule. And then finally, with this nice update rule, what we do is we apply it through the stochastic gradient descent update for Wi until our Wi converges to the optimum value, like in here. So that's it for this discussion video. Hopefully it helped, and see you guys next time.